Hi, let's continue with our section. In this video, we will do the anomaly detection with isolation forest. So anomaly detection is the identification of events in a dataset that do not conform to the expected patterns. So in applications, these events may be of critical importance. So let's write some text for that. So anomaly detection is the identification of events in a dataset that do not conform to the expected pattern. So in application, these events may be of critical importance. So for instance, there may be occurrences of a network intrusions or a fraud. So we will utilize the isolation forest to detect such anomalies. So isolation forest relies on the observation that it is easily to isolate the outlier, while more difficult to describe a normal data point. So, for example, we'll write some text. They may be, for example, they may be occurrence of a network intrusion or of fraud. So we will utilize isolation forest to detect such anomalies. So isolation forest depends on the observation that it is easy to isolate an outlier, while more difficult to describe a normal data point. So, and that is all in this video. So I hope you enjoy it and get excited. And I will see you in the next video. Hi, let's continue with our section. In this video, we will implement our anomaly detection with isolation forest. So let's import the library and the dataset. So first, we need to import the required library and set a random sheet. So we need to import numpy as np. So let's run the cell. So just wait for a bit to for it to have the connection, and we'll import pandas as pd, and we'll have the random underscore sheet will be np.random state, which will be drought. So we will create a set of normal observation to be used as a training data. So let's run the cell. And now we will generate a set of normal observation to be used as training data. So we have x underscore trend. So I just make small x, so it will be easier for me. So 0.5 times random seed dot run, and so it will create a random seed with find rate and then 2. So now we have x underscore trend equal np dot underscore, and then we'll have a x underscore trend plus 3 comma x underscore trend, and then we have x underscore trend equal pd dot data frame. So we have is x underscore trend comma column equals open brackets close brackets. So we have x comma y. So let's run the cell. So we don't have any mistakes. That is good. And then now we will generate a testing set also consisting of normal observation. So we will generate a testing set also consisting of normal observation. So now we have a result copy here and then base here. So we have x test equals 0.5 times random seed run find rate 2. We got x test equal x test plus 3, and then we got x test, and then finally we'll have is x test, and then we'll have x test. So let's run the cell, and we don't have any error. And now we will generate. So we will generate a set of outlier observation. So these are generated from a different distribution than the normal observations. So we have x underscore outlier equal random seed dot uniform. So we have low equal -5, high equal 5, and then we got side equal 50,2. And now we have is x underscore outlier equal bd dot data frame. So we have is x underscore outliers. So we have columns equal x comma y. So now let's take a look at the data we have generated. But first is we need to run the cell. And now let's take a look at the data we have generated. So we have percentage, mark, plot lib, and then we got inline. So we'll import mark plot lib dot plot as pt. So we got is p1 equal plt dot scatter. So we have a x underscore trend dot x comma x underscore trend dot y comma c equal white s equal 50, and now we have a ash color equal black. So we do the same thing. So just copy. We got a p2. So we got x test green, c equal green, s equal 50, and h color is equal black. So we got p3 equal plt dot scatter x outliers. So outliers dot x and then x underscore outliers dot y, c equal blue, and then h color is equal black. So now we have is plt dot x lim. So we got is negative 6 comma 6, and then we just copy and then paste here y lim, and then we have is plt dot legend. So we have is p1 p2 p3 comma, and then we will have is training set comma normal testing set, and then finally is anomalous testing set comma, and now we got is log equal lower right, and finally we'll have is plt dot show. So let's run the cell to see what is our plot look like. So we got the training is a y1. So it's very hard to see here. So it's around here, and the normal testing is around here, and the anomalous testing is very far away. So now we need to train an isolation forest model on our training data. So now we will train an isolation forest model on our training data. So we have is from sklearn dot ensemble, and then we'll import isolation forest, and now we have clf equal isolation forest, open bracket and close bracket, and then we have cls dot fit x underscore trend, and now we got y underscore trend equal clf dot predict. We have a x underscore trend. So we just copy 1 2 3, and then we got test, and then we will predict the x test, of course, and we got outliers, and then we will predict the x outliers. So now let's run the cell. And now we will see how the algorithm performs. Append the label to x underscore outlier. So now we have x underscore outliers equal x underscore outliers dot assign, and then we have is bread equal y underscore bread underscore outlier, and now we have x underscore outliers dot head. So let's bring to see what is. So our x is 3.9, y is 2.8, and now we got 2.97, and y we got 2.21, and then bread is -1. So now let's load the isolation forest prediction on the outlier to see how many it cache. So let's load the isolation forest prediction on the outliers to see how many it cache. So GHT, and we will review the code that we have done so far. So just copy this one and then paste here. So we have got P1 PLT dot scatter x trend dot x, x trend dot y, c equal y, s equal 50, and h color equal black. So now we will have is P2 equal PLT dot scatter. So we have a x underscore outlier dot log. So x underscore outlier dot bread equal -1, comma x comma, and we just shift copy and then paste. So x outlier, and then we got y, and then we got c equal blue, comma s equal 50, comma, and finally we have h color equal black. H color. So now we do the same thing for B3. So we just copy and then paste here. X outlier dot log x outlier dot bread equal 1. And then we got x outlier dot log is equal 1. X, Y, C bread s equal 50, and then h color is equal to black. So now we'll review our code in here. So just copy and then paste here. So we got plt.xlim -6 to 6, which is the same. So we got plt.legend p1, p2, p3. So this one is trending observations. So this one is detected. detected outliers, and the last one is the incorrectly labeled outliers. So log equal lower right, and then we got plt.show. So let's run the cell. So as you can see that our training observation is here. So detected outlier is here and incorrect label outlier is outside. So now let's see how it perform on the normal testing data and append the predicted label to the extent. So let's create a new code cell, and then here is now let's see how it perform on the normal testing data and append the predicted label to x underscore test. So now we have x underscore test equal x underscore test dot assign. We got Fred equal to y underscore Fred test, and now we got x underscore test dot head. Let's run the cell to see what is happening. So our result is very close. So 3.9, 3.8, 2.9, 3.1, 3.5, 2.1, except this one is very far. 2.9, 3.2, and then 3.2, and then 3.2. This is very close. So now let's plot the result to see whether our classifier label the normal testing data correctly. So now let's plot the results to see whether our classifier label the normal testing data correctly. So we'll review our code from the from here. So I just need the code. I don't need the comment. So just copy and then paste here. So now of course we need to modify some. So we got scatter xtrend.x, xtrend.y, y h black, and then we got p2 plt plus scatter. We got x test. So this one will be x test dot log, and then x underscore test dot bread equal to 1 x, and then we got x test dot log, and then we got x test dot bread equal to 1, and then y c blue s50, and then ash color is equal to black, comma. So I think I missed the commas, but it doesn't matter. This does not affect our result. So I just leave it there. So x, y, c equal red. It should be x. I think I missed here, so it should be B3. So I think it's a bit incorrect. So this one is So we got P1 x train dot y x outliers dot log x outlier breadth equal -1 xy x outliers dot log x outlier dot breadth -1. So C equal blue, S equal 50, H color black. And now we got PLD dot scatter x outlier dot log x outlier dot breadth equal to 1 x outlier dot log. So I think this one is a bit wrong. So hi, I did pause the video and try to find the problems, and it's actually not a problem because I did rewrite the code several times and try to rerun it, and I got the same result as the previous. So this one is correct. So we got the trend observation here. We got detected outliers and then incorrect label outliers, and that is the result that I got, and it's very close except the number 2. And this one is I just fix it. So it's just a x trend dot x trend dot y. So it's very similar from what we have done. And now we got the x test equal to x test dot breadth equal to 1, xy c equal blue, and we got scatter with the x test dot breadth is equal to -1, and we got x limit is -6 to 6, y limit is -6 to 6, and then we got training observation, correctly labeled test observations, and incorrectly labeled test observation. So we got the right in here. So the y1 is a trend observation, the correctly labeled observation is here, and the incorrectly labeled test observation is the red one. So what the is result show? So it showed that our isolation forest model performed quite well at capturing the anomalous points. There were a few false negatives instantly when normal points were classified as outliers, but by tuning the model parameters, we may be able to reduce this. So let's write our result. So let's write some note for that. So our model perform quite well at capturing the anomalous points. There were quite a few false negative. So which is the instances where normal points were classified as outlier, but by turning our model parameter, we might be able to reduce. So, but by tuning hyper tuning our models parameters, we may be able to reduce this. So I think this video is taking a bit long, and what I will end the video here, and I will see you in the next video where we will explain how does it work, and I will see you in the next video. Hi, let's continue with our section, and in this video I will explain how does it work. So I just delete the code cell and then write the text cell. So in step 1, wizard simply loading the library that will allow us to manipulate data quickly and easily. So in step 2 and 3, we generate a training and testing set consisting of normal observation. So step 2 and 3, we generate a training and testing set consisting of normal observations. So these have the same distributions. And in step 4, we generate the remainder of our testing set by creating outliers. So this anomalous dataset has a different distribution from the training data and the rest of the testing data. So this anomalous dataset has a different distribution from the training data and the rest of the testing data. So by plotting the data, we see that some outlier point look indistinguishable from normal points. So this one is step 5. So step 5. So this guarantee that our classifier will have a significant percentage of misclassifications due to the nature of the data. So, and that we must keep in mind this when evaluating its performance. And finally, in step 6, so step 6, we fit an instance of isolation forest with the 4 parameters to the training data. So note that the algorithm is fed no information about anomalous data. So we use our train instance of the isolation forest to predict whether the testing data is normal or anomalous, and similarly to predict whether the anomalous data is normal or anomalous. So in step 7, we plot the prediction of the. So in step 7, we append the predicted label to x underscore outliers to examine the how algorithm performs. And step 8 is we plot the predictions of the isolation forest instance on the outliers. So we see that it was able to capture most of the anomalies. Those that were incorrectly labeled were indistinguishable from normal observations. And in step 9, we append the predicted label to the X test in preparation for analysis, and then plot the prediction of isolation forest instance on the normal testing data in step 10. So let's create two more. So in step 9, we append the predicted label to X test in preparation for analysis, and in step 10. So let's go to step 10. So we plot the predictions of the isolation forest instance on the normal testing data, and we see that it's correctly labeled the majority of the normal observations. At the same time, there was a significant number of incorrectly classified normal observations, which is shown in red in here. And depending on how many false alarms we are willing to tolerate, we may need to fine-tune our classifier to reduce the number of false positives. And that is all in this video and also in this project. So I hope you can get the same result as me, and you can perform successfully the isolation forest with the anomaly detection. And I will see you in the next video.